And ladies and gentlemen, thanks for joining me on this last Tuesday of October. Today I'm going to be talking about this thing called the Weibull distribution. So today's conversation does involve a little bit of prior understanding, but if you've never heard of the Weibull distribution in the past, don't worry. There'll be precious few equations. In fact, I don't know if we have any, which is always what students want to hear when going to talk about statistics and randomness and probability and things like that. Now, the Weibull distribution is used a lot in reliability engineering, and a lot of people know why, but a lot of people also don't know why, but don't care. They just go through the process and trot out the Weibull distribution and use it in whatever way, shape, or form a textbook tells them to use it to generate a number which gets fed to the decision maker, the boss, the manager, and all as well. But that's not really what we want to be doing when it comes to the Weibull distribution. We actually really want to understand how this thing can help us, specifically in the world of reliability engineering, and how it can make us look a lot smarter than your average reliability engineer, which is ultimately what we are all about, obviously tongue in cheek. So let's look at a random process, and here is my apparently now world famous random hand of failure, the hand that represents all the multitude of different factors and uncertainties which turn what is essentially a physical process into an uncertain process. Even though we know how things fail, we know that corrosion is oxidation, which is accelerated by H2O molecules, etc., etc., etc. Problem is, even if we know it to that extent, there are always variations in factors which govern that chemical reaction, or that fatigue crack growing, or that rubber perishing, and so on and so forth. So we have to unfortunately deal with random processes when it comes to reliability engineering, which is really, really struggling because it is a problem in that our relatively primitive human brains actually aren't really wired to deal with all the nuances that reliability and statistics and probability throw our way. So from this random hand of failure, we might observe some data points. And what I mean by that is we might conduct a test, and each one of these blue dots on the line represents a specific instance or a specific time to failure of a product. So let's just say there's 30 blue dots on the line. That means that we might have conducted a test where we monitored 30 different products, and we worked out exactly when each one of them failed, and that time to failure is represented by a blue dot. Now you can see we have behind those blue dots this orange shape, this bell curve looking thing. That's what we call the probability density function. Now, a full description of the PDF probability density function is outside the scope of today's conversation. However, you can see that the height of this PDF curve seems to correlate with the region where these blue dots occur the most frequently, where the density of those blue dots is the highest. And that's what the probability density function curve is. It tells us the relative likelihood of random variables having certain values, which is why the higher the PDF curve, the more likely it is for you to see blue dots where the highest point of that PDF curve occurs. Now, for this PDF curve, it's a bell curve. Most of us have heard of this thing called the bell curve, and I've done plenty of other webinars which actually look at this bell curve in greater detail, and I'm not going to go over that in great detail today. However, if we know what we're looking for as reliability engineers, which we should be, we can see that this has a peak. This looks like a mountain, and every time we see a PDF curve which has a peak, we know our system is wearing out. That is because of the underlying statistics, and we can certainly go through and prove why that's the case. But the main takeaway from this lesson and lots of other, this conversation, lots of other conversations, is that we shouldn't just be looking for numbers or metrics or things like that. We should be trying to see what is going on. And if we create a PDF curve, we see a PDF curve which describes time to failure, and that PDF curve has a peak, has a hump, has a top, an apex, whatever you want to call it, it tells us straight away that our system is wearing out. And that means that our system is accumulating damage over time in a way that adds up. Now, this is not the only way our system can wear out. So for example, let's say I conduct another reliability test, live test, and I get these 30 data points here. You can see the original bell curve still there, but now we have a different PDF curve. It is shallower. It's not as nearly as high. It's more spread out, but it still has a peak, not a particularly sharp peak, but it certainly has a peak, a maximum. And again, that tells us that our system is wearing out. But if you know what you're looking for, you can see that because this PDF curve has a left skew with a right tail, sort of smooshed to the left, good reliability engineers will be able to see straight away that our system is wearing out, but the damage is multiplying over time, like a fatigue crack, where the longer the fatigue crack gets, the faster the fatigue crack grows. So the rate at which we accumulate damage multiplies as we accumulate more damage. Then we have this PDF curve here, which is a very different looking PDF curve. This PDF curve is anchored at the vertical axis where the time to failure is equal to 0. It has, it's not 0, it's not infinity. And it has a gradual but consistent exponential slope. And this is what a PDF curve looks like if our system is failing with a constant hazard rate. There is no peak. You don't count the anchor point to the vertical axis. That's not the peak. There is no peak. And you can see the curve is constantly going down. So this is what happens when our system has a constant hazard rate. And as opposed to our wear out systems, it means our system is never accumulating damage, so it never gets old. And conversely, it never gets better. So a 100-year-old system is just as likely to fail today as a brand new system. Let's look at another PDF curve again. You can see that the data points are moving when we have a look at this fourth and final PDF curve. This PDF curve hugs the vertical axis. It goes all the way up into infinity. It's not anchored. It goes all the way to the very, very top, so to speak. It hugs the vertical axis and has a very steep slope, which very early, but it has a much more shallow slope later on. Now, this PDF curve tells reliability engineers, tells good reliability engineers that our systems are wearing out or experiencing infant mortality. And that means that we have a subset of, let's call them imperfect systems. And those imperfections, those defects, those assembly errors, those crystalline dislocations, whatever it is that is affecting a smaller subpopulation, those are creating what we call early failures. And once our system is able to get through that initial period, the apparent reliability increases. Now, these four PDF curves, each one of them represent a different failure mechanism, which is really, really useful. And every single one of these curves is generated from this distribution called the Weibull distribution. The Weibull distribution is loved by reliability engineers across the world because it is a single distribution, a single way, a single model that allows us to understand characterize different ways our things can fail. And if we have a very complex system, we're going to have hundreds of thousands, if not millions, of different failure mechanisms. And with that level of complexity, we need to really simplify how we look at failure in order to make better decisions. So here are four instances of the Weibull distribution. You might notice that you can see the bell curve, which some of you might think looks a lot like the normal distribution, and it does. The other wear out curve, the second one from the right, so to speak, that mimics the log normal distribution. And we're going to go into this in greater detail. It's just Weibull distribution is really, really good at modeling lots of different, very different failure mechanisms. And one additional feature of these four probability density function curves is that they all have the same mean. All the same mean time between failure. Now, the mean is a hypothetical balance point of these PDF curves if you turn them into an actual shape. And this is one of the many reasons why the mean or the mean time between failure is not reliability. It often feels like it's reliability. The MTBF has the word failure in it, so therefore it has to deal with something to do with reliability, surely. And of course, if the reliability is high, there is a general relationship with the MTBF such that the MTBF would also expect it to increase. But you can see that these 4 PDF curves have model very different failure characteristics or failure processes, but they all have the same mean. So you cannot just be given the mean, for example, the hypothetical balance point, and then make really crucial decisions that are based on the shape of your PDF curve if the only thing you have is the point where it would hypothetically balance. But nonetheless, the fact that these 4 PDF curves are fantastic at modeling different failure mechanisms means that because they all come from the same distribution, the Weibull distribution itself is very, very useful. So I've just said that all these PDF curves are from the same distribution, but you can see their shapes are very, very different. So where do these shape characteristics come from? Or where does the overall characteristics of any Weibull distribution comes from? Well, every Weibull distribution is defined by 2 parameters. The first parameter is called the scale parameter or the characteristic life. And that just gives us an idea of how long something's going to last. A typical unit's going to last for something which is experiencing, obviously, a random failure process. So the scale parameter, in a way, just adjusts the magnitude of the random variable or tunes the magnitude of the random variable. The second parameter is the most interesting of all. It's called the shape parameter. It doesn't have any units associated with it. And this shape parameter is what allows us to model all sorts of different scenarios. If the shape parameter is less than 1, we know that our system has a decreasing hazard rate. Now, what that means is that functional or working systems are less and less likely to fail, provided they're still functioning. That's what wear-in looks like. And this is typically what we see when we have those subpopulation of imperfect products that are being essentially weeded out in that early period of use. Then we have scenarios where the shape parameter is equal to 1, and that implies a constant hazard rate. That's where things never get old, things never get young. And whenever the shape parameter is greater than 1, things are wearing out. We have an increasing hazard rate. Damage is being accumulated. And so this makes this shape parameter extraordinarily informing. It's one of the most important parameters in the world of reliability engineering, because not only does it help us fine-tune the Weibull distribution in lots of different scenarios, that single metric can tell us if we need to walk to the manufacturing line because we have quality control issues. It can tell us if we need to walk to the design team because the design life does not meet the customer or user mission profiles. And if it's equal to 1, we know there's a constant hazard rate, which typically means it's failing due to randomly occurring external stresses. So let's look at one of our original PDF curves from the start of this conversation. This is a Weibull distribution with a shape parameter of around about 3.5. And it looks a lot like bell curves or normal distributions. The hazard rate for a system which is generating these data points, which are clustering around this region here, is this red line, the rate at which a thing that is still working fails. And so when damage adds up, we have an additive wear out scenario, like where our tires are wearing out, for example, we see this sort of phenomenon. So that's one example of how the Weibull distribution can model a very specific type of wear out. This type of wear out is modeled by a Weibull distribution with a shape parameter of around 2. And like I said, it looks a lot like some log normal distributions, which are fantastic at modeling, for example, fatigue, things where the damage multiplies up over time. The wear out, it tends to be relatively straight. Sorry, not the wear out. The hazard rate tends to be relatively straight over time. And for fatigue and corrosion and creep, we often see these sorts of Weibull distributions do a magnificent job of modeling times a failure. Here is that Weibull distribution, which is where the PDF is hugging the vertical axis. That means we have a shape parameter of 1, which is better known as the exponential distribution. And so one specific example of the Weibull distribution is the exponential distribution, where the hazard rate remains constant. Things are not getting old, not getting younger or better, and that means failures are being caused by catastrophic environmental stresses, those things that when they do come along randomly, they're so catastrophic that your system entirely fails. A really good example in electronic componentry is voltage spikes. When you have a 6,000 volt spike come through your power supply, doesn't matter how old or young that capacitor is, it's about to have a very bad day. And then finally, this is what the Weibull distribution with a shape parameter of between 0.3 and 0.5 looks like. And empirically, and based on some theory as well, we know that virtually every wearing scenario has a shape parameter of 0.3 and 0.5. So if you're having quality control issues, if you're having assembly issues, or if you're trying to manufacture, let's call them troublesome electronic components, where it's just very difficult to create perfect crystals in your silicon chipsets, you would reasonably expect to see a shape parameter of between 0.3 and 0.5. And that's very useful, because if we see this sort of hazard rate curve, this wear in, we know straight away where we need to look at, or where we can start focusing our attention on improving reliability. We don't, if we're seeing a decreasing hazard rate, there's no point going to our customers or users and saying they're using the thing in the wrong way, or that the end of life wear out failure mechanisms are causing problems, or whatever else you might initially instinctively look towards, as opposed to what is actually causing failure. So the Weibull distribution can help us tell if our system is wearing in, wearing out, or doing none of those two things, i.e. it has a constant hazard rate. And most failure mechanisms have their own shape parameter. So let's look at the Weibull distribution in a little bit more academic, with a bit more of an academic mindset. So here are those 4 example PDF curves. One thing I have changed here, as opposed to them having all the same mean, they now all have the same scale parameter, the same characteristic life. You can see on the right-hand side that the eta value for each one of these PDF curves is 12. The shape parameter for each one of these curves is different. We have one where it's 0.5, one where it's 1, another one where it's 2, another one where it's 3.5. So these are all Weibull distributions, which clearly model very different failure scenarios, but they all have the same scale parameter. They are, of course, all Weibull distributions. And so this is one of the most useful ways of understanding or characterizing uncertainty. This is the way that the human brain is best wired to try and either visualize or conceptualize the uncertainty of the world around us. If we look at the bell curve in the middle, that green curve, that is typically what our brains are hardwired, instinctively wired to characterize uncertainty. We have a typical value. In this case, it looks close to 12. And then we have uncertainty either side of this typical value. That's how our brains are wired. If someone tells you that their best guess at something is 12, our brains automatically, in a way, superimpose a bell curve over that best guess. So we say, okay, Tim said his best guess was 12. Therefore, it is most likely to be 12 according to Tim, and it's less likely as we move further and further away from 12 for that value to be correct, just like that green bell curve. But there are 3 other PDF curves here which are very, very applicable to the world of probability and statistics, which our brains are not wired to conceptualize or understand. So the PDF curve is the closest thing we have to being able to talk directly to our brains using our highly developed visual senses to conceptualize uncertainty. But the PDF curve is problematic because it's really hard to get meaningful numbers. And that's where it becomes this thing called the cumulative distribution function becomes really, really useful. Now, the CDF, or the failure function, gives us the failure probability of our product or system at a particular point in time. And that is where we start being able to take an understanding of the uncertain world around us and turn it into meaningful information to make better decisions. So the CDF is also the area under the PDF curve. The PDF curve, when you think about it, all that area under the PDF curve does is essentially allocate the relative likelihood of each one of those random variable values. So the area under that PDF curve tells us what the probability that our random variable is going to have a certain value between certain numbers. And so the area under our PDF curve gives us the failure probability at a particular usage. So let's use these PDF curves to generate CDF curves for the Weibull distribution. Now you can see for the bell curve, or I might go back one and pause it there if I can. Oh no, my animations are going to mind of their own. So they're going to do it no matter what I say. So I'll have to give a preamble. What's going to happen is for each one of these PDF curves on the left-hand side, you're going to see the area under each one traced out from left to right. And the amount of the area is going to be scribed on the blank set of axes on the right-hand side. So as you can see that, when we create these curves, that the area is going to be analogous to the height of the curve in this blank right-hand screen right now. Now, because my animations have been set up by this human, and ideally I'd do it in a different way moving forward, just focus on the animations you're about to see, and hopefully they'll illustrate the construction of each one of our CDF curves. We'll start with that bell curve. You can see the areas being traced out. And you can, so my speakers decided to change. I don't know if I'll be able to hear you if you guys reach out, but I'll, oh no, I'm back. My hearing's back, but my audio, I've had some audio issues at my end for a while. Okay, so sorry for that IT issue, but you can see that by tracing out the area under each one of these PDF curves, we created a CDF curve corresponding to each one of those parameter pairs. So the green line represents the green bell, or is the CDF curve for the that's from the Weibull distribution, which gave us the green PDF curve or bell curve on the left. Now you should be able to notice something amazing. See that each CDF curve goes through the same point. So the CDF curves, these CDF curves on the right, which represent the probability of failure as our things get older. And as you can see, they start at 0, which implies that our system is working at time equals 0. And as our system gets older, the probability of failure increases all the way to 100%, which essentially just means each one of our systems is going to eventually fail. But for these CDF curves, they all somehow manage to go through exactly the same point. Now, some of you might have noticed that this is not just coincidence. You can see that that point where they all go through is actually above the characteristic life, or the shape parameter. Where the shape parameter is 12, the CDF for each one of these Weibull distributions appears to be exactly the same. We're going to come back to this observation a little bit later on, because it's very, very useful. But before we do that, let's look at another function that describes, helps us characterize the random process that is failure. And that is the reliability function, the probability that your system has not failed at a particular time, usage, or specified condition. It is simply 1 minus the probability that your system has failed, or 1 minus the CDF. So if we are able to trace out our CDF curves, well, our reliability curves are essentially our CDF curves upside down because it's 1 minus the CDF curve. And you can see, likewise, our reliability curves all go through the same point at this at a characteristic life of 12. There's a reason for this, and that is because here is the one of the very few equations you're going to see in this conversation today. This is the function. I can see there's a couple of questions coming up from William, one from William about the point at which it crosses over. I'm going to answer that question very, very shortly, because you can see that this is the equation for the reliability of the Weibull distribution. You can see where the two parameters exist. You can see the eta and beta are in there. You can see T represents the time to failure, and we have that weird number E, or Euler's number, which is at the base of that exponential function. Now, a detailed description of the Euler function, Euler number is outside the scope of this webinar, but it's an incredibly useful number, which allows us to, for example, create functions like this, which allow us to directly incorporate parameters we care about, like beta and eta. So if the system has reached its characteristic life, what that means is T is equal to eta. So let's get rid of every single T from the equation, the reliability equation above, and replace it with eta. So now we have an equation which gives us the reliability at time is equal to eta, or the characteristic life of the scale parameter. You can see on the right-hand side that we now have eta over eta, which is equal to 1. So let's substitute 1 into there. We simplify our equation. We also know that 1 to the power of anything is 1, so we can get rid of beta over here. And now we have simply E, or Euler's number, to the power of 1. Negative 1, I should say. And that, when you ask a computer to evaluate for you, is 36.788%. And that means the reliability of any product whose time to failure can be modeled with a Weibull distribution will be 36.788% at the characteristic life. Or another way of saying exactly the same thing, the CDF will be equal to 100% minus 36.788%, or 63.212% at the characteristic life. That makes it really handy later on, and we'll come back to that little coincidence that the Weibull distribution has given us. So there is the reliability function. You can see that the reliability function for any system starts at 100% and goes all the way down to 0. Essentially, it means that our systems will eventually fail. Now, there are some scenarios where the reliability function doesn't start at 100%. It starts at a lower number. Is anyone willing to hazard a guess as to why that might be the case? Feel free to throw your answer or your guess in the chat window. Why might there be some reliability curves that do not start at 100%? Is there any reason why we might not have a reliability curve starting at 100%? Maybe this might help you. Is there any reason why we can't assume that every single system is working at the start of its useful life? Pre-aged item, fantastic. Perhaps it's been given to somebody else after it's been gone through some burn-in, and perhaps it wasn't properly screened. A hot spare, it's been used and now it's being taken off wherever it's being, it's a redundant component, and now it's been brought on back to life. And it might have already failed. Maybe it was losing life before the beginning of use. Fantastic. You talk about previous operational use. Fantastic. We call these things, or variations of these things, dead on arrival factors. And they're not just caused by those scenarios, but they're also caused by, for example, your product being shipped to a customer or user and being treated in a very, very nasty way by your distributor. Perhaps the mailman or mailwoman dropped the box containing your priceless smart device, and that drop meant that your smart device that you're hoping was going to work when you opened that box, when you got home from work, because it's sitting outside your front door, is now broken beyond recognition because the delivery people didn't do a good job. Now, that might seem like it doesn't count, but it certainly does count. And that's why we need to take make sure we design not only robust systems, but robust storage and packaging and handling. So what do we call those? That material, which makes sure everything is looked after when it's being posted from one point of the world to the other. It's also kind of a big deal for satellites. When you have, for example, a bunch of small satellites being launched en masse in the residual payload or bay of a spacecraft, most small satellite launches involve a pretty well understood 15% dead on arrival rate. It's something the industry is trying to work on, but it's still definitely a thing. So the hazard rate, though, I just left that topic way too early. So that's the reliability function. The reliability function, which usually starts at 100% and eventually goes down to 0. And you see with the Weibull distribution that every reliability function of any Weibull distribution has a value of about 37% when it reaches its characteristic life. The last function I want to talk about is one of my favorites, the hazard rate function, the rate at which a thing that is still working fails. The way we calculate that is simply divide our PDF by our reliability function. PDF gives us our density of failures. The reliability takes into consideration how many systems are still working. And so all we need to do to generate a hazard rate function for a Weibull distribution is essentially divide the height of the PDF curve by the reliability function. And so for all those example Weibull distributions we looked at so far, you can see on the left-hand side, the PDF curves and the reliability functions are superimposed. We get these 4 very different hazard rate curves for each one of those scenarios. And that is at the heart of the Weibull distribution. It's a very, very flexible, very, very useful distribution or model that helps us really understand and characterize a vast array of different failure mechanisms. And so this means we don't need to have a huge library of models, a huge library of distributions to cover the overwhelming majority of real-world failure mechanism scenarios. And not only that, the Weibull analysis that I talk about in other lessons, it doesn't even matter if your process is modeled by the Weibull distribution or not. When we use Weibull analysis, you can actually suck out all sorts of useful information, even when the data is generated by another distribution. That might sound mind-blowing. It's simpler than it sounds, but certainly outside the scope of this conversation. But it's one of the myriad of reasons that reliability engineers love the Weibull distribution. It can model a single distribution, can model so many different scenarios. And so those are the 4 main functions: the PDF, CDF, reliability function, and hazard rate function. Now, there's one other characteristic we need to be aware of for the Weibull distribution, and that is the mean. The mean is not an obvious quantity from the shape and scale parameters. You can see the equation for the mean here. All this equation is how somebody worked out what that hypothetical balance point is for every single Weibull distribution PDF curve. And you can see that we have the shape parameter, the scale parameter, this weird Greek uppercase letter called gamma, which represents this thing called the gamma function. And the gamma function is illustrated beneath the equation for the mean of a Weibull distribution. And the correct response to seeing that equation is shock, alarm, dismay, perhaps PTSD, I don't know, but that particular function is not possible. It's not possible for a human to evaluate that function using nothing but their brain and paper. And so the Weibull distribution mean needs to be calculated with the help of a computer. Here are 2 Excel formula you can use. Use the bottom one if you need to identify the Weibull distribution mean, and you have Excel 2003 and earlier. These functions and a formula are in the workbook, which the link to it has been provided by Fred in the comments window. So that's an overview of the Weibull distribution, but we're not done yet. because Weibull distribution allows us to do this thing called Weibull analysis. And Weibull analysis is tremendous. Why is that? Oh, come on, computer. Because this is one of the ways we can look at data and without equations having to do anything challenging or anything really, I wonder where that tomato comment came from, Fred, thank you. It allows us to look at data and without having to use equations, suck out a lot of information. Now, I run a lot of courses, and the thing that piques the interest of my students the most is phrases where I start with, we're not going to use any equations. So let's look at a scenario where we have our random hand of failure, which represents all the different uncertainties and factors of a specific random process. So let's just say we got a product and we're going to examine its time to failure. Or more specifically, we are going to examine the time to failure, the failure characteristics of many products or several products. So this is the random hand of failure number one. Now let's just say that these data points were what we observed for that first random hand of failure. You can see they tend to be centered around the middle, which is good. That's often how our brains like to characterize uncertainty. And let's just say that although we don't know it at this stage, this random process is modeled by a Weibull distribution with the shape parameter of 3.5 and a scale parameter of 1. Let's just say that. Now, in the real world, we don't know what that distribution is. It's actually very hard for us to be able to see what's going on when we have nothing but those data points on the horizontal axis. We might have some idea if our process was modeling things like wear out, because we might know using our huge brains that wear out involves the addition of damage over the time, which means that we're looking at a bell curve-like process or bell curve-like PDF, and we know that the Weibull distribution, the shape parameter about 3.5, tends to mimic the bell curve really well. But that might be as far as we go. We might have no idea, as a rule, we have no idea about the failure process that's given to us, that is presenting a bunch of seemingly random data points. So let's do the same thing for another product or another process with this other random hand of failure. And it produces a lot of data points, same number of data points. But this case, the underlying process for this random hand of failure was caused by Weibull distribution, or modeled, I should say, by a Weibull distribution with a shape parameter of 1 and a scale parameter of 0.6. So we know straight away this has a constant hazard rate, which could be caused by voltage spikes destroying electronic components. But of course, this is invisible to us when we do a test. All we get is a bunch of red and blue data points. And here's a third random hand of failure. And you can see, oh, geez, something weird's going on there. Got 30 data points. And if we're able to look inside the failure process, we might be able to see that this thing, or we might be able to see it, but if we were to hypothetically, magically look into the failure process, we might be able to determine that the shape parameter is 0.4 and the scale parameter is 6 in this case, which means that because beta is less than 1, we know this failure process is being dominated by wear in. But of course, again, we will never know what those distributions are, those potential models that describe our 3 different failure processes, that if we knew what those failure processes were, we might be able to answer lots of really important questions. So if we are faced with just this spreadsheet of numbers, so to speak, how can we learn about these random failure processes from this messy bunch of data points without complicated equations, i.e. without this guy? This guy is the ponderous professor that in my other webinars I introduce as one of the many enemies of reliability, the guy who wants to make things more complicated, the guy who wants to analyze until he is happy, not necessarily when the decision needs to be made, et cetera, et cetera. And so how do we look at these data points without our ponderous professor over our shoulder, without complicated equations, and actually get something useful? Well, the very first thing we might do is might transform our visualization from one where we just have those data points sitting on the horizontal axis to one where we have a vertical axis now introduced, and the height of that vertical axis represents the percentage of things that haven't failed. So as we have, I think we have more than 30 data points. It looks like closer to 100, to be honest, but nonetheless, so we have 100 data points for each process. You can see on the left-hand side, very start, everything's working. So each data point, in a way, starts off at 0. But as things fail, percentage of things that haven't failed, sorry, this shouldn't be percentage of things that haven't failed. It should be percentage of things that has failed gets higher and higher. So on the left-hand side, you can see percentage that haven't failed. That should be percentage that have failed. And that number gets higher and higher and higher and higher over time. Now, what this does is smooth out our data visualization so we can see trends, we can see different shapes, and that's quite useful to a point. Whenever we can smooth stuff out, that helps our brains visualize what's going on. But can we work out if a Weibull distribution can apply to any of these? The answer is no. And if we assumed a Weibull distribution could be applied to any one of these, how do we get those parameters? Those eta and beta parameters, which help us understand the nature of failure. Well, I'm going to hit the transform button. The transform button means allows me to take this particular axes where we have the percentage of things that have failed, or should say, on the vertical axis, and time to fail on the horizontal axis, and change the scale of each one of these axes in a way to produce something really special. So I'm just going to hit that button. And then what's going to happen thereafter is those scales will change the way I suggested to create this thing called Weibull probability plotting paper. You will see that on the horizontal axis, we now have a logarithmic scale. Each red line on horizontal, each red line moving horizontally represents a factor of 10 increase. So you can see those green lines on those vertical green lines that hit the horizontal axis. They represent a logarithmic scale, represent our time to failure, I should say, on the logarithmic scale. The vertical axis is still the percentage of things that have failed, or the CDF, but there is now a really weird scale. And that scale is based on math. It's based on some equations, which I'm not going to go through today, because all you need to know is that this curiously scaled piece of paper, or curiously scaled chart just is perfectly designed such that any data generated by a Weibull distribution will create a straight line. So this is what this is one of the very powerful uses of this thing called Weibull probability plotting paper, is that if our process, our failure process, is described well by a Weibull distribution, you'll see straight lines. And yes, these are straight lines. I know they're not straight perfectly, but in the world of probability and statistics, this is what straight looks like. This data set was generated by me. It was artificially synthesized by 3 Weibull distributions for those parameters I gave you before. So you can see that there is some variation in what these straight lines look like. That's only because failure is a random process and each data point is a random variable itself. So even though there is some variation, these lines are what we, for all intents and purposes, straight. And so I can walk away from this Weibull plot and conclude the Weibull distribution is a pretty good model for each one of my 3 failure processes. Now, the next thing I can do is remember how the CDF is always 63.212% at the characteristic life. Well, you can see that that horizontal blue line right there represents when the CDF is 63.212. So now I can just draw a line straight down from my data lines, so to speak. And those lines that go straight down allow me to estimate the scale parameter for each data set. All those scale parameter is essentially the point by which 63.212% of my things have failed. So without having to do any equations, I now have an estimate for the scale parameter. But it gets better yet, because the slope of these lines is going to tell us the most information about our failure process. So you can see here, we have 3 lines of best fit from our data sets. The blue data set, the slope is the steepest. The green data set, the slope is the shallowest. And the reason being is that each one of these slopes represents the shape parameter. So the green data set, which is from the wear-in process, which had, as you might recall, we were able to magically know that the shape parameter was 0.4. It has the shallowest slope. The wear-out data set, the shape parameter of 3.5, has the steepest slope. And so if you're able to do Weibull probability plotting, then you can create these lines, and you can, without having to do a single equation, estimate the scale and shape parameters. And now you might be somewhat intimidated or challenged by the whole act of doing that magical transformation, taking data and putting on these really weird axes, these really weird scales. But it's actually a lot simpler than you think. And there's a lot of help you can get out there from software. Perhaps you can get too much help, so to speak, because there's a lot of software where you just put the data in and it will create a Weibull plot for you. And if you don't know how the software got to its conclusions, all you turn into is a piece of software yourself, where you're just looking for a number to put into a report to make the problem go away. If you understand what the software is trying to do and how the software generates these lines and these curves and everything else, then you become way more powerful, because you know what these things mean. And if you know what these things mean, you're able to see really, really useful characteristics in your failure process, which could just happen to save millions of dollars for your production process, or prevent any number of crises which would otherwise blow out your schedule, etc., or without using a single equation. So that is why the Weibull distribution is really, really powerful. So let's just do a little bit of revision. I'm going to use Weibull analysis in the context of this smart lock. Smart lock is one of my centerpiece examples in my webinars and lessons. And it's a wonderful example of a system which involves electronic componentry, traditional mechanical lock technology, material science, so on and so forth. Virtually every technology you can think of in today's sort of manufacturing and design context is either represented directly or pretty close to being represented in contemporary smart locks, because they have these wonderful array of very different components. So our smart lock has 17 components. 16 of them are different, if you count the 2 different door handles as being the same component. And let's just say that we have conducted Weibull analysis on our bolt mechanism, and the Weibull analysis suggests a shape parameter of 0.4. What sort of things might be causing our bolt mechanism failure, if that's what our Weibull analysis is suggesting? It has a shape parameter of 0.4. So anyone who wants to hazard a guess at what might be causing failures for our bolt mechanisms, please ensure that they're not tomato-related failure causes. I'm only just talking to you, Fred. What sort of things might be causing these bolt mechanisms to fail if we have a shape parameter of 0.4? Assembly fault, manufacturing defects. I wouldn't say life exposure wear, William, that's sort of rather broad, but if you're talking about the sort of typical wear and tear you get over the useful life of a system, probably not, because a Weibull shape parameter of 0.4 implies our thing has a decreasing hazard rate, which means that as our smart lock gets older, provided it's still working, it's less and less likely to fail. Yep, some really good examples there. Again, I wouldn't suggest constant wear and tear. Oh, no worries, all good. Inspection misses, fantastic. Some way, shape or form, a number of imperfect bolt mechanisms are getting through to the end. Now, why is this really, really cool? Because it means that from a number, we know we're experiencing wear in, or that we have a decreasing hazard rate. And some of the suggestions you came up with were fantastic. But straight away, I'm going to be looking for these sorts of things that are causing the failure of my bolt mechanism: manufacturing problems, assembly error, damage during transportation. And not only that, if I'm a good manufacturer, if I'm trying to break into the market, I need to make sure perhaps that I come up with a robust design that mitigates these factors from the very start. For example, if I'm concerned about these defects being caused by incorrect installation, and to the extent that I need to pay a certified installer to install these smart locks in these consumers' front doors, so to speak, is that design a good design? Is a design where you need to pay someone, pay a homeowner, or pay someone to install that lock into a homeowner's front door, is that a good design versus another design where the homeowner with his or her minimal skill sets is able to relatively easily install a smart lock without causing wear in, defects, damage, what have you? So it's not just manufacturing per se. Sometimes we need to go straight to manufacturing. But if those causes are based on things that we can't easily change, like the customer expecting to be able to install this him or herself, then we might need to go back to design. William suggested foolproof the installation. Exactly. We might need to find a way of making this really easy to install. So let's look at some other parts of our smart lock. Let's just say we've conducted Weibull analysis on our LED and teeny tiny speaker. And that Weibull analysis for each one of these components suggests a shape parameter of 1.0. What sort of things might be causing our LED or speaker to fail? So what guesses do we have what's causing our thing to fail if the Weibull analysis suggests we have a shape parameter of 1.0? Go a little bit deeper on this one. These are electronic components. What does bad component mean in this context? Hit by a tomato. Yes, Fred, I concur with that. If those tomatoes are occurring at a relatively constant rate, I know in Spain the likelihood of being hit by a tomato goes up remarkably during 1 week of the year. But in this case, occasional big door slams like that one, random manufacturing. No, I can't agree with the random manufacturing defects because you'd see a decreasing hazard rate, current spike, surge, short circuit, which would be causing those things. Fantastic. So what's happening here is that our LEDs and speakers, if they have a shape parameter of 1.0 and they're not being hit by Fred's tomatoes, are not getting older, they're not getting younger, they're not getting better. They have a constant hazard rate. So if they're not getting better, so to speak, we can relatively comfortably, with some caveats, conclude that there is not a wear-in failure mechanism. There's not defects, because as your system ages, you'd expect these failures to decrease the rate of failures to decrease over time. Also, wear and tear is out, so to speak, because if the hazard rate is constant, it's not getting older. And so those things like shock loads from door slams, those voltage spikes, those single catastrophic external environmental stresses that when they occur, ruin the day of your LED and speaker, those are the sort of things we're looking for. And now this is fantastic design information, because without having to do root cause analysis, where you're for LEDs, good Lord, you can only imagine what that looks like, where they have to, cut the LED, the silicon wafer, and it just sounds horrible. And same with the speakers. How would you do root cause analysis and you send it off to a lab and they come back and tell you, well, this thing broke? You don't necessarily need to do all that, because if you have a shape parameter of 1.0 and it's an electronic component, I'm looking straight away for voltage spikes and surge protection. If I think long and hard about how this door is being used, is my door being slammed in a way which is not ideal, but unfortunately, it's how our customers are going to use our smart lock, so to speak. And so these are the sort of things I'm looking for straight away. I can rule out certain things. I can and focus my attentions on things that are going to matter. And I can do that within an hour. So, for example, I can issue an edict to, or not an edict, that sounds very authoritarian, but I can ask the electrical engineering team, say, hey, what voltage or surge protection do you have for the LED and the speaker? If the answer is none, I need to tell them almost straight away, well, we need to have some in there, because initial testing suggests that voltage spikes are one of the likely root causes of failure. Conversely, if we're able to look at and see if there's mechanical damage, you might be able to go straight to, oh, there's some sort of shock loads being transferred. How do we transfer shock loads to a lock which is embedded in that door? We slam the door. So straight away, that little number tells me exactly, well, not exactly, it gives me a really good idea of where I need to start looking in order to improve failure. Now let's look at another component of our system, the handle. And preliminary Weibull analysis suggests a shape parameter of 2.1. What sort of things might be causing our handle to fail if the shape parameter is our best guess? The shape parameter is 2.1. So do your thing. Weather and pressure applied, cool. More of a wear out, concur with that. Wear due to turning, I'm guessing. The key thing I'm picking up from the responses is that cycles is how we measure time. Sort of, I'm guessing you're talking about the accumulation of the effects of cycles, door opening in that regard. But if you are all talking about the accumulation of damage, we are experiencing wear outs. Long story short, an increasing hazard rate, then I fully and wholeheartedly agree with you. Now, some causes for wear out are listed on the screen right now: glue degradation, fatigue, corrosion, socket plastic deformation. And if we've done a FMEA, for example, the corrective actions for all these root causes of failure might already have been done for us. We just now need to go and implement them. And so this just goes to hopefully illustrate just how important that single number can be if you understand what Weibull analysis and Weibull distributions can do for you as a reliability engineer. And I want to leave you with the message that measuring reliability is important, or can be important, but it's not nearly as important as making reliability happen. So on that note, are there any questions about the Weibull distribution, the little taste of Weibull analysis I gave you, and reliability in general? Any questions at all? Thank you, Anna. That wasn't a question, so it's disqualified, but I'm very glad you wrote that nonetheless. What about combined Weibull plot breakpoints and segments? So, William, that's a good question, and the answer to that is somewhat outside the scope of this webinar, but I will try and do some scribbling and maybe come back to it. Let's see if I can get my Weibull plot. So let's just say, William. Oh, yeah, that's a good one. I'm going to start drawing on this. So here's a Weibull plot, and you have three beautifully straight lines, so to speak. Now, if you see a Weibull plot and your data points trace out a line which looks like something like this, you can see that we have sort of down here a shallow slope, here a steeper slope, here a much steeper slope. You can almost see that we have different regions on our lines of best fit, so to speak. And of course, those are lines of best fit of a bunch of data points. So we're talking about, I'm using blue data points, and it's not the best because I'm drawing using some of the limitations of a PowerPoint presentation. But if you see a Weibull plot like this, where it's not a single straight line, but bunches of multiple straight lines, well, all is not lost. I think Adiol is asking the same question, multiple failure modes, because down here we have a wherein. Oh, sorry about the quality of my writing. Wherein failure. Right here, we might have constant hazard rate failure. And up here, we have wear out. Now, you might be able to look at your data and say, okay, I believe that the transitions between these phases are here and here, and that's fantastic. So this can help you, for example, work out when you're servicing intervals should be. You shouldn't service, if this is a product which you service or replace or swap out, you should never service it within this window here, because in this window here, there is no wear out. Not wait, out. There's no wear out in this interval here. So you know your servicing should be roughly about there. And that's pretty rough, but it's not to be honest, that sort of analysis is a lot more than most organizations do when it comes to maintenance. Now, hopefully you can understand the scribble I've put on this Weibull plot. So that just shows you how you can have multiple failure modes apparent on a Weibull plot. You can't use a single Weibull distribution to describe the entire system. And what many awful reliability engineers tend to do is just get lazy or not understand what they're doing. And they just say, oh, okay, so there's a bendy line. I'm just going to find the line of best fit through all this data set. And instead of having 3 line segments, they go, well, I'm going to draw a single line of best fit. And often that means that results in a single line of best fit, which has a beta value of approximately equal to 1. And they say, okay, the system has a constant hazard rate. It's never wearing in, it's never wearing out. Therefore, shouldn't service it. We shouldn't do anything. But in fact, if they looked a little bit deeper, they would realize there's 3 line segments and not just one really oversimplistic line of best fit. Now, I'm going to another webinar, which I routinely give about how to interpret Weibull plots, which is outside the scope of this conversation today. But I do think it's important for you to get a taste of what the art of the possible is and why the Weibull distribution, which enables all this, is really powerful. I can see that Bill asked also how we get the eta value or characteristic life. I'll just go to the slide that helps us do that. Just as revision. Oh no, that's, oh geez, sorry about that. That slide there. That's how we estimate the eta or characteristic life or scale parameter, where if we have data creating lovely straight lines, that's the first caveat, and those straight lines go through that horizontal line, which represents 63.2%. If you scroll right down, then let me get a different color. I'll go back to red. Right here, that might be, I don't know, let's just say that's 10. That's not going to be that. That might be 18. That might get on the horizontal axis, that might be 22. That might be 31. And so that tells you how it's that is a way of graphically estimating the scale parameters directly from your Weibull plot. Hopefully that answers your question. And David points out that failure analysis is always important in untangling combined failure data. Yes, if you can get a root cause analysis, if it's, you can work out, what's causing each one of these data points to fail at the very start, that usually makes analysis really easy, or a lot easier. But if you don't have that information, all is not lost. That Weibull plot, those different failure modes can be really, really easy to identify and helpful for a lot of decision making. Any more questions or comments? Is it used to run multiple? I just want to make sure I understand the question. Is it used to run multiple Weibull analysis using? Is it useful to run multiple Weibull analysis using different etas or etas? I don't fully understand that. For example, when you run when you run an analysis, part of the analysis is to work out what that eta value is. So the analysis will give you the eta value as opposed to using a different eta value. So I'll probably need you to clarify. William Harwood asked, will a best fit line always show constant failure rate? Absolutely not. For example, you can see if you might remember, the slope of these lines gives you the shape parameter. And so you can see that depending on you've got 3 different lines of best fit, only one of them implies a constant failure rate. Only one of them will give you a slope of exactly equal to 1. So a line of best fit will help you work out what the shape parameter is, and it could be anything. Thank you, Michael, for that feedback. So can we use Weibull with only one failure mode? The technical answer is yes, you can only use a Weibull distribution to model one failure mode, but it's really easy to combine the two. You have to use what we call system reliability modeling, where we combine more than one basic event, so to speak. So it's quite possible, but a Weibull distribution, a single Weibull distribution, can only model a single failure mode. That's your question. That's the answer to it. Thank you for that feedback, David. Much appreciated. Thank you, Bill. Is there software or application that will break down complex Weibull plot or data? The answer is yes. I don't want to badmouth any one of them, but and there are one in particular is not bad, and I don't want to advocate. I'm about to say give all these things mixed reviews, so I don't want to drop names. It's just inherently challenging. I do it, but I don't use software. It's quite a few things you need to look for when you do the analysis, and it might sound trivial, but it's not, especially when you need to create things like confidence bounds or use that to work out, optimize servicing intervals or things like that. And the software packages that I'm aware that do this, that are out there, as a minimum, they recommend having 100 data points. And so that's not always useful, especially if you're interested in the first few failures, which as a rule most of us are. There's options besides ReliaSoft, and yes, ReliaSoft is one that can do multiple failure modes and mechanisms. Again, I really don't want to get into doing the pros and cons of software packages right now. If that might be frustrating for listeners, and it's one of the reasons why I do it all with my own MATLAB coding. But there are things you need to be looking for, and if you just do a data in, data out approach or numbers out approach without understanding what those pitfalls are, you're just asking for trouble. And as a rule, again, I'll go back to those. The first few data points are usually the most important. And so you might only need to introduce or create a Weibull distribution for the first 5% of your failures. And that's all you need, because you're not interested in working out when the last of your 1 million devices are going to fail. You need to know when the first 5% are going to fail, because that's what your warranty period allows you to do. Allows your company to tolerate. And so even if your system has multiple failure mechanisms and multiple failure modes, which it will, you might only be interested in modeling the failure mode which dominates the first 5% of failures. And so that's almost, it's a scenario where you have multiple failure modes, but using a single Weibull distribution to model the one of those failure modes. And that's, I don't know, that's sort of a rambling answer, but it is challenging to get software out there to characterize multiple failure modes in a very automated way. And if you do, you need to have, as a rule, 100 or so data points, which means you need to have no suspended data points. So you need to test everything till failure. If you have a service life of 10 years, good luck getting that information. So it's a challenging question to answer in a very fair way. The technical answer is yes, you can do it, but you need to be experienced and know what you're looking for to make sure you don't make any incorrect conclusions. I'd second the comment William made regarding R. Not a problem, Satya. Have we exhausted our questions? Are we done? Or are we just exhausted? The answer to that question, Jay, is yes. This webinar and presentation, along with all other webinars, and I dare say, are you referring to accompanying workbooks or notes? They are always posted on the Ascendo website. It's just a matter of time it takes for us to get produced and then uploaded. Thank you very much. So we're starting to get a lot of thank yous, a lot of well dones, which usually means there are no more questions to be asked. That said, if we finish today's conversation and you walk away and then you think of an amazing question, please feel free to reach out. You've got our contact details. But thank you very much for turning up and supporting what we do at Ascendo, and looking forward to seeing you my next webinar. I got it wrong last time, and Fred, I had to change the sequence. So what's my next webinar, Fred? I've got it here. Let me pull it up. My next webinar is about something amazing. That's all you need to know. Not true. It has I really need to get slicker at this. It is why redundant systems aren't always redundant. We talk about how you can seemingly invest a lot of money into creating a redundant component, but it doesn't deliver the reliability performance you are hoping. Okay, Fred, I think we're done, unless I've missed any questions that you might have picked up on. Please forward any tomato-related questions to Fred. I like tomatoes in terms of eating them, but I prefer other people to make the stuff. That's how I use tomatoes that I use for tomatoes. So on Weibull, he's looking. A lot of corporate knowledge about tomatoes waiting to be unleashed on the Ascendo crowd. Okay, I think we're good. Thank you very much.